In this video, I will share what is meant by a parallel plate capacitor and what is the expression for capacitance of this capacitor. First of all, let us take the construction of this parallel plate capacitor. As the name implies, this capacitor consists of two parallel plates having equal area of cross section. These plates are taken very thin. These are held parallel to each other. Suppose area of cross section of both the plates is equal to small a. Both these plates are held at some distance. Let us suppose this distance is d, and a slab of some dielectric medium is held in the space between the two plates. The area of cross section of this dielectric slab is also kept same. This whole thing which is appearing in this diagram is called a parallel plate capacitor, and one of these plates is charged positively and the second plate is charged with the same magnitude but opposite in sign, that is minus q charge is given to second plate. Let us suppose T is the thickness of dielectric slab that is held between the two plates. So the whole space between the plates can be supposed to consist of two parts. One part of thickness T, that is slab, and second part of the capacitor can be supposed to have dimension d minus t, because the total dimension is d. After subtracting this thickness, we are left with d minus t, this space and this space. And there will be electric field between the two plates because both are equal and oppositely charged. Let me suppose in this space, that is in space d minus t, electric field is E naught. Here also it will be E naught. And inside the dielectric slab, let me suppose electric field is E. Now we have to find the values of these electric fields. E naught can be written as sigma over epsilon naught, where sigma is surface charge density of each of the plates and sigma is defined as charge per unit area. So I can write by q by a epsilon naught. So we are left with q upon a epsilon naught. So this is the value of electric field in the space d minus t between the plates. Similarly, within the dielectric slab, electric field will be E. It will be calculated later on. Now let me find electric potential. Electric potential in space d minus t, means in the space except this dielectric slab. Let me call this potential as V1. It will be E naught multiplied by d minus t. Where from this relation has come, we know the definition of potential gradient, that dV by dr is numerically equal to electric field. So using this, we can write potential difference equal to E multiply dr, means electric field multiplied with distance gives us potential. So this is how we can find potential in space d minus t. After putting the value of E naught from here, I can write V1 is equal to Q upon epsilon naught A d minus t. So this is the potential in the space d minus t. Similarly, we have to calculate potential within the dielectric slab. If E is net electric field inside the slab and E naught is externally applied electric field on the slab, then dielectric constant of the material is defined as K is equal to E naught divided by E. So this will give us value of E as equal to E naught divided by K. So this is the electric field within the space T. Using this, I can find electric potential in this space. Electric potential in space T. Earlier we have calculated electric potential in space d minus t. Let me call it potential V2. It will be E multiplied with T. Again, by using the definition of potential gradient, potential can be written equal to electric field multiplied with space. After putting the value of E, we can write V2 is equal to E naught by K multiplied with T, where K is dielectric constant of the dielectric material. Again, let me put value of E naught from previous equations. So I can write V2 is equal to Q divided by K epsilon naught A multiplied with T. So this is potential in space T. Earlier we have calculated V1 as potential in space d minus t, rest of the space. So total potential between the two plates will be sum of V1 and V2. Total potential between two plates of capacitor V is equal to V1 plus V2, where V1 is potential in the space d minus t, V2 is potential within the space t. After putting the values of V1 and V2, I can write V is equal to Q upon epsilon naught A d minus t plus Q upon K epsilon naught A multiplied with T. After simplifying, I can write V is equal to Q upon epsilon naught A taken as common inside d minus t plus t upon k. This will give us answer for Q upon V is equal to epsilon naught A divided by d minus t plus t upon k. By definition of capacitance, Q over V can be replaced by C, that is capacitance of the capacitor, equal to epsilon naught A divided by d minus t plus t upon k. So this is the required expression for capacitance of a parallel plate capacitor having a dielectric slab of thickness T held between the two plates. By putting various values, we can calculate capacitance of this parallel plate capacitor. That's all.